In this problem, we have a sphere of mass m with charge positive q on it. The sphere is in between parallel plates with equal and opposite charges or surface charge densities. And our sphere is hanging from the ceiling by a thread, and the thread is making an angle theta from the vertical. The distance between the two plates is d, and the question is what must be the potential difference between the two parallel plates given the variables in the problem. So how do we solve this problem? Yes, if you're thinking this sphere is in equilibrium, that is correct. So we are going to apply Newton's first law on the sphere. And what is the first thing we need to do? We need to draw a free body diagram for the sphere. So let's go ahead and do that. Here's my free body diagram with my sphere at the center as a dot, treated as a point particle. We have three forces acting on the sphere. Gravitational force F sub g is pulling down. Tension force F sub t is pulling at an angle, following the direction of the string. And finally, we have the electric force F sub E in the horizontal direction, pulling to the right. Now, how do I know that the electric force should be in that direction? First of all, where does the electric force come from? It comes from the electric field between the two parallel plates. And the electric field in between the plates is going to be uniform. That we know. And we know that the electric field is going to be horizontal. Now, if the electric field is horizontal, electric force will be horizontal. And the only way these three forces can balance out is to have an electric force pointing to the right. Otherwise, there would not be any balance or any equilibrium. We want the net force to be equal to zero, right? So we want the horizontal component of the tension force to be cancelled by the electric force. So the only way to have that is to have an electric force pointing to the right. Now let's go ahead and set up our equations, our force equations, applying Newton's first law in both directions, in the x direction and in the y direction. So I start with the equation F net equals 0 equation in the y direction because we have less unknowns in that direction. Basically, we just don't know Ft. The rest is known. On the other hand, in the x direction, we have both Ft and Fe that are unknown. At least for now, we need to, it's not obvious what they're equal to. So that's why I'm starting with net force in the y direction equals 0. And then, based on my free body diagram, I expand the net force side on the equation. And again, this Greek letter, capital sigma, that means sum. So sum of the forces in the y direction equals 0. So I have the y component of Ft pointing up. So that's positive. That's plus Ft cosine theta minus Fg, because Fg is pointing down, equals 0. Now, you may be asking, where does cosine theta come from? Why is it Ft cosine theta? Well, if you look at the picture, I have shown the y component of Ft with this vertical dashed line, the blue line, that represents the y component of Ft, and that's basically the adjacent side for the angle theta. That's why we use cosine theta for that. Now, let's also substitute the formula for Fg. What's the formula for Fg? That's m times g, mass times gravitational acceleration. Let's substitute for that and isolate Ft, because that's our unknown. We want to isolate it. And in the next equation, next force equation, we are going to eliminate F sub t. And here I have Ft isolated. It's equal to mg divided by cosine theta. Next, we apply Newton's first law in the x direction. So net force in the x direction equals 0. And what are those forces? Again, based on our free body diagram, we have the x component of Ft pointing left, so that one has a negative sign, plus F sub E, the electric force, pointing right, so that will be a plus sign. Now, what's the x component of Ft? Again, I highlighted that with the orange dashed line, the horizontal orange dashed line on my picture, that is the opposite side from the angle theta, so that's going to be sine theta. So negative ft sine theta is the y component of ft plus fe equals 0. Again, let's rearrange our equation to isolate ft. Also, what is F sub E, right? Well, again, the electric force comes from the electric field, and on a point charge, the electric force is going to be equal to electric field magnitude. So this is the magnitude, by the way, of the electric force, because we have already determined the directions, negative, positive directions in our force equation. So everything is going to be positive. Every substitution will be positive after this point. And the magnitude of Fe, the electric force, is equal to the magnitude of the charge times the magnitude of the electric field. So that's going to be Q times E. I'm going to make that substitution as well in the next line. And here I have another expression for F sub T. It's equal to Q times E, E being the magnitude of the electric field divided by sine theta. So I have two different expressions and both are equal to ft. So let me set the right hand sides equal to one another, because I don't know ft and I'm not interested in it. So I'm going to set the right hand sides equal to one another, and also express electric field magnitude E in terms of the potential difference, which is what I'm looking for. So let's do that next. Here I have combined the two equations to eliminate F sub T. Now, how is electric field E related to potential difference delta V? Let's remember that. And here's how they are related. The potential difference between points A and B is equal to the negative of the line integral of the electric field along the path from A to B. Okay, so now do we really need to take an integral in this problem? Not really, because in this problem we have a uniform electric field, so that comes out of the integral, and the path integral or line integral of dl is simply the distance d. Okay, so in this case delta v is equal to E times distance d, and I'm going to keep delta v positive, so I'm really just going to calculate the absolute value of potential difference. So I'm going to keep everything positive, and here's what we get if we simplify this expression. So the absolute value of the potential difference is equal to the electric field magnitude times the distance d, but that's the distance between the two plates. Now let's isolate E from here so we can substitute this expression for E in our main equation on the left hand side. E equals absolute value of delta V divided by D. And this makes sense. Remember, what's another unit for electric field E? That's volts per meter, right? So electric field tells us, or the magnitude of the electric field tells us, as you move from point A to B, like how much the potential changes, how many volts the potential changes at every meter. Okay, so that makes sense. So the potential difference divided by D, that's electric field magnitude. Now let's substitute this in our main equation. Here's our equation after the substitution, and as the final step, let's rearrange this equation to solve for the unknown delta V. Here's our final answer. The absolute value of the potential difference between the two plates can be expressed as mgd tangent theta divided by q. Where does tangent theta come from? Well, I have sine theta over cosine theta, so I replace that with tangent theta to make the expression look a little simpler. Now you may be asking which plate is the high potential one and which one is the low potential one. Let's take a look at the picture again. We can see that the sphere is being attracted towards the plate on the right hand side. The sphere has positive charge, so that the plate on the right hand side must have negative charge, and the plate on the left hand side must have positive charge. And the positively charged plate is the high potential one, so this is the high potential one, and the negatively charged one is the low potential one. So as you go from left to right, the potential decreases. And what's the direction of the electric field? Remember, electric field points in the decreasing potential. So the electric field points right from the positive plate towards the negative plate. And remember, the force on a positively charged particle points in the same direction as the electric field. So the direction of the electric field, that makes sense. Both the electric force and the electric field point to the right in this problem.